My name is Merrick. I'll be presenting my paper on detecting distributed immune systems through the use of an artificial immune system. Okay. So just to an overview, I'm going to work through the problem background, then we're going to look a little bit at artificial immune systems themselves, and then the immunology background that they're based on. Then we'll look at the model that I created, the base model. We'll look at the prototype that was based on the model, and then the results. So if we look at the problem, in terms of the problem background, technology is more and more widespread every year. Important systems that run critical functions for companies, for countries themselves that you live in, are all run on computer-based systems. And I mean, this is great. It means that there's less manual intervention, etc. But at the same time, this creates vulnerabilities. And these systems need to be protected. But if we're considering some of these systems, they're also interlinked. So we cannot consider them as siloed systems where I can take this system by itself and I can take this one by itself, because if we look at the country's infrastructure, if the power grid goes down, or if the water system goes down, or if the communication goes down, there's a knock-on effect to everything else. So we need to consider protecting everything on a holistic point, on a holistic level. Now, the idea in doing this is, why not draw parallels between how the biological immune system protects the body in a distributed manner to distributed computer systems. So let's first just take a look into immunology and understand roughly how that works. Basically, we look at three high-level types of immune protection that the biological immune system works on, which is your anatomical barriers, which are kind of physical protections. We can't really draw parallels to that in terms of the artificial immune system, because that's more a physical protection. Could just be kind of actual security on a site where the computer system is. Then you've got your innate immune system, which is any immunity that is kind of inherited from your parents, etc. And these are basically against known threats. But the biggest problem generally is not against known threats, but rather unknown threats. Many antivirus software protection mechanisms make use of databases where they've stored signatures of what a virus looks like, and they protect you against that. But the problem is, zero-day threats mean they haven't seen this before, it comes along, and now you have a problem. And that's where the adaptive immune layer comes in, and that's where the focus of this is. And obviously there are many theories and models around how the immune system really works, and people debate this, but there's some base immune entities that are part of it all. And that would be your antigens and your pathogens that make up the immune system, and various cells that function within that. Very well known, and a lot of people would have heard the terms, are your B cells and your T cells, which generally inside the immune system are responsible for detecting and dealing with threats that are found on a very high level. And the idea of this is, once a B cell finds something, it attempts to bind with it. Now this binding process is based on chemical signals and based on the shape of physical shape where it binds. And the idea is, when that happens, it releases signals which are little molecules into the body that signal the T cells to come along and take care of the problem. Now the T cells themselves also have to be able to bind to the problem, so it's kind of a two-factor test. In case there's some abnormalities there, and after this there's other signals are created that cause the body to create memory of this problem that was found. And the idea is that that memory is then used for any further incidents that it can respond more quickly. Now, in terms of an artificial immune system, we want to be able to replicate this in a way, so we need to be able to try and detect threats that we previously have not encountered, and also obviously store memory of them for later incidents. idea there is to be able to is to be able to store, to be able to detect these new threads, and then obviously signal for them to be taken care of, and then allow replication of the memory to other nodes across our distributed network. So it can all be protected as a whole, and that we can allow all the various entities within the system to also migrate between different nodes. So we do not just contain everything to the part of the system where the incident was found, but rather it will spread and protect everything else in case the thread also tries to propagate. So the base model that we came up with is basically a three-layered approach at implementing this kind of protection, where we kind of look at it at three high-level layers of, firstly, the immune process. So what are we actually basing our artificial immune system on? As I said, there are many different immune models and theories, and they can't necessarily all be implemented at the same time, and some feel that it's best to use one or not. Obviously, this is where you can decide where you want to put in what you need, but the whole idea is that this is responsible for defining the overall higher level of how the immune system functions, and how the different entities within the immune system are created, etc. Then we've got our immune agent layer. This is where we actually define the agents themselves. So this is a multi-agent system where we're going to have singular agents that are of different types, and they all function autonomously, doing their own thing, but we need to be able to define what are they capable of. A B-cell agent, for instance, cannot terminate entities or get rid of things within the system because that's not its job. It is there to only detect threats and signal and create memory, whereas the T-cell would be able to do other functions. And then on the higher level, we have the distributed agent management network, which is basically the layer responsible for helping coordinate agents across this distributed system, how they can migrate, how they can communicate, because they need to communicate across various nodes, and also for the termination and also the redundancy of the system. So for instance, if something goes wrong in this node and all the agents there get wiped out, we need redundancy so that it's now not completely unprotected. So spoken through this really. We've spoken through most of this. The real idea is that by defining these various high-level layers, we can come up with the actual implementations of what we need to get done. So we need to define the models on the immune system layer and what entities it involves. We need to be able to define exactly which agents and what capabilities the agents have on the agent layer. And then on the agent management layer, we define kind of an agent platform and rules around this and how agents can move and communicate and how we can facilitate all of this. So the prototype system that I created based on this made use of negative selection, creating B-cell and T-cell entities so we can detect what's going on and deal with it. And then for the generation of new entities, as we need this to continually evolve and change, we do not want the population to stagnate. Some genetic algorithm for the evolution and creation of the population of agents. And then on the agent layer, we made use of B-cells and T-cell agents, so we kept it very simple in that way. We do not need molecules that tell them how to communicate, because they can directly communicate due to the third layer, where we have our Jade agent platform, which allows us to create multiple containers. These containers can be distributed across physical hardware systems and logical networks, and still operate and still have agents within those containers operate and communicate as if they were on the same machine. And the whole idea is that we also have multiple containers for failover redundancy. So if one container goes down, then another container is spawned to replace it, and with multiple containers on each node, there should never be a case where there is no protection on a specific node. From a high level, if we had an antigen or a threat, we've got our agent that will attempt to bind with it. Now, in terms of drawing the parallel between the molecular binding that happens in the immune system, for the purpose of this, made use of a string detection algorithm based on the hashes of items within the system to determine whether something is part of the self set or not. And if it was part of the self set, then obviously it would not be bound to, because the detectors were trained on this. And if it was not part of the self set, based within some similarity, then it would be bound to. It would send a signal to the killer cell or killer agent, which would then also attempt to bind. If that binding did occur and was successful, then it would take care of the problem. On a higher level, understanding how this would kind of fit all together, we've got our distributed system across the multiple physical and logical locations, connected through some kind of network. And within that, we've got our various different agent platforms on each location, and within them containers that contain of the various different agent populations, allowing us to replicate agents and have memory of what's going on in all around the system. So in terms of results, we looked at measuring this on kind of 3 metrics. One being obviously its capability to detect threats, because without that it's kind of pointless. But at the same time, a system like this would also be fairly useless if it was very impactful on the systems in terms of performance. So looking in terms of CPU usage and memory usage, what is the impact of this? In terms of testing, multiple test runs were done per testing metric to capture averages, just to make sure that obviously we don't have any outliers, etc. So in terms of threat detection, over multiple runs done, an average of around 70% was obtained, which is fairly good, I'd say, for a rudimentary model. And this held also over larger test run sets. It was just easier to graph it out this way. In terms of CPU usage, we can see that, so basically here we're looking at the number of agents that are generated, because the more agents we have in the system, the better. But the problem is the more agents we have running in the system, because of how they're implemented, means that they make use of more processing time so that they can actually perform their job. Now, I tested this on a few increments of agents, which I found would fall within realistic expectation. And obviously as expected, the CPU usage would go up as you introduce more agents, but then also calculated what is the actual CPU usage per agent as you go, and it does tend to tail off as you get higher. So it is not an exponential increase. As you keep increasing, it will keep increasing. It increases to a point, and then per agent it does tail off. In terms of memory, the same thing. We also don't want to have something that uses up all the computer's memory and then since they're thrashing. So the same test was run, but now measuring memory, and the memory usage also had the same trend of initially using more memory as you go, and then tailing off further. And yeah, on a high level, that's it.
Well, thank you. So other questions?
If I may ask something related to the 3-layer model, and when you are on the input system level, and when you use the genetic algorithm for the generation of the generation, are you working with fixed number of entities, for instance, the cells are the same number already? I mean, when you regenerate, or the next generation? Are they the same number of entities or the population change varies?
No, so the population will vary and change. It's not fixed.
It's changing, and
Yes.
exactly. And then what controls the population cardinality change? What determines that how many elements will be in the new population?
So it was limited to a range of entities due to impact on the system. So as we saw from the graphs, that obviously as more entities or more agents are introduced into the system, the performance of the system will be impacted. So it was just kept within a range of between 100 and 400 for
So it was almost rule control or something
yeah,
like
rule
that.
control to that extent, but within
Then
that,
this range.
within it there was randomness
Uh-huh.
for how much actually existed.
And then the system performance was projected back to the number, if I understand you
Yes.
correctly.
Yes.
The performance of the system was projected back.
Thank you for the presentation. So how large is your network then, and in what type of application did you use your model or your proposal?
So this was implemented over, so for the prototype, for the actual testing.
Okay.
This was implemented over a small network of, I think it was 5 computers.
Okay, yeah.
Obviously just for testing purposes.
Sure.
Couldn't get hold of too many more, but yeah.
And you think it could work also on the larger networks?
I believe so if some optimization for the exact problems are done and there's a lot more work to put in, but on a theoretical point of view it should.
Yeah.
Right. I have also a question. Do you also think about autoimmune diseases? That so the learning from the nature is great, but there are
yes,
some.
that can be a problem. Obviously, as we see, the biological immune system isn't perfect, and it can actually be its own worst enemy at times. Exactly. Basically, we can look at controlling that better with defining different methods for matching. And combining kind of, let's call it, like the kind of string matching approach with also behavioral matching, which would help reduce that a whole lot more. As if something is acting incorrectly and it doesn't look as part of the cell.
So you wouldn't run into the same problems as with antibiotics?
I don't know what an antibiotic equivalent would be.
Antibiotics are,
Yeah.
you know.
I'm saying I don't know what the equivalent would be.
There are resistant diseases which you cannot treat anymore.
Yes, yes.
That's the background of the question.
So I mean, the idea is that within this we try to differentiate from the self and the non-self. If the self is measured on a fairly consistent basis where it is known to be certain kind of a snapshot and it doesn't vary much from there, then anything else that should be introduced thereafter would be detected and should, yeah. Obviously there's many intricacies that we could go into.
So maybe,
Question, because otherwise we miss the bus.
yeah, so maybe just adding my 2 cents to your question about autoimmune diseases. So the terminology in artificial immune systems is called immunological hold. And it's effectively very briefly touched on when he talks about a zero-day exploit. It's effectively having an antivirus where there's no cure for it, no way to detect it. So normally what you would do if you deploy something like this in a multi-agent system environment, you'll have like a kind of like a, call it a checker agent, where you obviously measure the internal utility of an agent, but also from a holistic point of view, you need another agent who's going to check if all these other agents are performing their task and if not. And if that falls below some predefined threshold, it's a quick and easy way to just say, well, then there must be an autoimmune disease within the system or this ecosystem.
We're done. Okay.
Okay, so as the time is approaching, we don't have unfortunately time for further discussions. Ingrid just told me that the bus for the hotel will leave in about 10 minutes. So I want to thank you again. See you later on.